Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer, and it's so nice to see you again. I hope you guys can see and hear me okay. With any luck, this is going to work out just fine. But anyway, it's nice to talk to you all. I have, been a little bit busy lately, getting with school and all that kind of stuff, trying to convert that to an online format, and I am now finally getting back to doing something I've been wanting to do for a long, long time. Because undoubtedly, this is the 50,000th time you've heard, "Oh, we're living in strange times." Yeah, but you know what? This is streaming on YouTube. We're just hanging out, having some fun, talking about the kinds of subjects that inspire us and get us excited, and basically just kind of keeping our brains alive a little bit. Before I bring on my guest, I'd like to just welcome a few folks here. I want to say hi to Paul Peck, Drywall Tube. Good to see you. Piper Trip. Good to see you, buddy. Raj Luthra, thanks so much for dropping by. Urban Explorer, always a pleasure to see you. Derp, and let's see, of course, Cool Worlds, and Atom Synergy. There he is. Okay, so I'll be saying hello as things go on, but I'm pretty rusty at this, so I'm going to try to do this without making too many mistakes. But ladies and gentlemen, please welcome my guest, Dr. David Kipping, from the channel Cool Worlds. David, how are you?
I'm doing great, Christian. Yeah, thank you so much for having me. It's really such a pleasure to get to have little breaks and just talk about space and think about much more cosmic things for a while. I mean, so much going on right now. I really appreciate this time to zone out and just talk about space.
Yeah, thank you, David. I appreciate you coming on and helping me with this. Like I said, it was something I've been wanting to do for some time. I know that Omad here says he's a huge fan, and so am I.
Thank you.
Yeah, well, David, every time you upload a video, all I can think of is, wow, I really suck at this. This guy is really awesome. This guy over here. So, uh,
That's kind of like how the old joke of how like with inventors, but if you look at like Edison or someone, you look at Edison like, oh my God, he made so many inventions. As an inventor, I feel like a failure compared to Edison. And then I think there was a funny Simpsons episode where in Edison's laboratory, he had a chart of all the inventions that Leonardo da Vinci had. And so everyone's always looking at someone else
oh
saying,
yeah.
oh, if only I could be as successful as that person. And I think that's a rat race. Just I try not to worry too much about that, but it's easy. It's an easy trap to fall into.
So as we're chatting, David, I'm getting some comment here on can I bring up? Okay, so David, it sounds like your sound is a little bit low. So I want to see if there's something that I can do.
I'm going to
Uh,
step a little bit close to my mic. I'm going to put my volume as right up as I can, and hopefully this is a little bit louder now.
okay, I hope that's coming through a little
If
bit
this is still a
better.
problem, I can switch them. We have two mics, so I can switch the mic. This
You
is
can, but you know what? I don't know if this is on you. I think this might be on me. I may have a way. Okay, this volume is way too low, so I think I might have a way. And thanks everybody for your feedback. I assure you, as I get the hang of this, I ought to be able to. Okay, well, hang on. I'm going to fix the volume here. QC1, okay. Can I watch with Dave's volume being too low? I gotcha. I gotcha. Let's try this instead. So I know that if I bring this up, ooh, I'm way too loud now. I know that if I bring up my microphone, you can hear me, right? I'm assuming you guys can all hear me now. The clicking is comments on Christian's and it's off the desktop. Okay. So you're hearing my clicking, I apologies. Okay, so I'm hearing, wow, no audio. Sorry about that. Let's see here.
We'll get there.
Yep.
Don't worry.
You could just
Still part of
you could just let them know in the chats. You could say, "Hey, we're working on it."
Yeah, I'll say hi to the guys on the chat.
Thank you.
I'm gonna be chatting on here.
Change because it ought to be. Now I'm using my own microphone as my audio output. I bet you can hear me now.
So it sounds like you're okay.
You can hear the clicking, but no sound. How mild clicking, but your voice is much louder, which is good. Right, so my voice should be louder because I just switched to this microphone as my primary output. But what I thought I was doing was using the microphone to talk to Zoom and then letting Zoom's audio go into the stream. And that does not appear to be working, which is very odd.
I've just switched my mic over just in case that makes a difference.
Mm-hmm. Okay, so Deja hears me. Can you all hear David?
There's David just really quiet, so they can hear me a little bit. I should start shouting.
They're probably getting you in my microphone here, which is not what I wanted. I'm really sorry about this, guys. Just one more thing I'd like to try.
Okay, so they can sort of hear me.
Yeah, so we're back to...
We could even just call it in, and put like a phone next to it.
I guess, but they're not picking up the Zoom audio. Okay, so Urban Explorer is yelling at me to leave it like this, mate. Okay, fine. All right, well, I apologize once again for the audio problems. Like I said, this is a little bit like just figuring out how to ride a bicycle. And we will definitely be improving this. And David, I promise we'll have you back on when the audio does get completely sorted. But still, I think we can go ahead and continue for now. So, David, I did just want to say though that I really enjoyed your latest video. But first, before we talk about videos and the Fermi paradox, all that kind of stuff, for those like maybe one or two people watching who don't know about your channel, can you tell us a little bit about yourself, the kind of research you do, and what your channel is all about?
Sure. I'm an assistant professor in the Department of Astronomy at Columbia University. I joined Columbia 4 years ago, and as soon as I started, within about, I think it was about 6 months to a year, I started the YouTube channel. And that was always something, even when I was applying for jobs and interviewing at Columbia, I was like, I'm going to start a YouTube channel because I really believe the future of scientific communication is going to be online increasingly. And we're seeing that accelerate, obviously, right now, everything that's been happening. And I think it was motivated a little bit by, I've been doing a lot of public speaking events where you go to maybe an astronomy club in New Hampshire, or you go to visit, you do like a lecture and people buy tickets and come and hear about astronomy.
Mm-hmm.
You're kind of preaching to the choir a little bit. I mean, most of the people that are willing to surrender their evenings, find childcare to look after their kids whilst they go out. Those people are very, very passionate about astronomy already. And my dream was to reach to a broader audience and to try to tell everyone how amazing exoplanets are and give them some direct insights into research as well. So we tried to really talk about most of the research we do in my group on exoplanets. We do make videos about them. And recently we've been making videos about related topics as well that we think about a lot as well. So I want you to get into the head of an astrophysicist and to see how we work and to demystify some of that process.
Oh, fantastic! And so you mentioned that you were really doing a large part of your research. You said was based on exoplanet research, right?
Yeah.
Yeah.
So we work on a bunch of stuff to do with exoplanets. The thing that we are most well known for as a research group is I work on exomoons,
Mm-hmm.
moons around planets, and so far we only really know of one candidate exomoon, which is
Right.
actually one that we discovered and did some videos about. And this has been almost a career-long passion, almost a lifelong passion, a career-lifelong passion for me. Ever since my PhD thesis, my thesis was all about how to developing the methods to look for exomoons, and it's been something I've been following out since. At the same time, we do increasingly more and more diverse research as well. Right now, we're thinking about planets in a galactic context, which actually has some relationship to my last video.
Mm-hmm.
Rather than just looking at the direct solar neighborhood and the planets which are really close by, let's think about planets across the galaxy. Where can planets live and maybe not live? How does that affect the habitable zone of even stars around galaxies, for instance? We've been thinking a lot about using machine learning methods increasingly, especially a technique called natural language processing that we're trying to apply to exoplanets for the first time. And we've also been looking at the TESS data, which is just coming through. So TESS is the new
Right.
space telescope, which has been detecting and measuring many exoplanets through a transit method. And me and my team have been looking at that data very carefully. We actually have a paper that just came out that Tiffany Jansen led on WASP 100b, detecting a phase curve from TESS for that. She's actually hopefully going to do a video about that
Oh,
soon.
cool. Oh, great. Yeah, I mean, it's funny how exoplanets were all the rage, and then they kind of ebbed off for a bit. And I think with tests now, we're looking at getting potentially 20,000 to 200,000 new exoplanet candidates. I think it's going to suddenly start coming back into vogue quite a bit. Uh, but, and interestingly enough, you're talking about exomoons, and I thought we could just talk a little bit about that for a moment. You did
Sure.
discover, or you have a detection, I guess, on the first exomoon candidate. But as I recall, this is not your average moon, and I was wondering if you could tell us why.
Yeah, it's a pretty strange object. The thing that's most surprising about it is its size. If this moon is real, it would be a Neptune-sized moon. And obviously there's nothing like that in the solar system. I mean, there's Neptune-sized planets. Uranus and Neptune are both Neptune-sized planets. But to have a moon that big is pretty surprising. The planet it goes around is also a little bit odd, but not as surprising. It's a super Jupiter, as we would call it. So it's a planet which has about the same size as Jupiter, but it's more massive. And perhaps that makes sense as to why it might have such a large moon. And the orbit of the moon around the planet is probably in many ways the least surprising aspect of it. It looks very much like the Earth-Moon system, just scaled up.
Right.
You just sort of did Honey I Shrunk the Kids in reverse and just sort of blew it up.
Honey, I blew up the kids.
You
Yeah.
pretty much get this system. It has the same mass ratio, the same radius ratio.
Yeah.
It has the same major axis and units of planetary radii. So everything is really like a scaled up version of the Earth-Moon system. However, we don't think this looks likely to be formed in the same way that the Earth-Moon is hypothesized to have formed.
Right.
As probably many of the viewers know, the Earth-Moon system is thought to have formed through this giant impact. So this Mars-sized body, sometimes called Theia, may have smashed it into the early Earth, knocked off a lot of the debris of the Earth, and that sort of coalesced and formed our moon. Now this is a gaseous planet and a gaseous moon, so that seems a bit odd to make sense, because when you have gas and fluids, that's going to dampen the collision, and you wouldn't expect it to sort of graze off and coalesce in the same way. So its origin is still mysterious, and even the reality of this moon is still unclear. But I like to often remind exoplanet folks that the first discovery of an exoplanet around a normal star was equally very surprising. And I'm sure you remember this, Christian.
Oh, yeah.
When 51 Pegasi b was announced. I was still in school when 51 Pegasi b was announced, but I still remember it being a shocking story, because it was a Jupiter-sized planet almost on top of its star.
Yeah.
It's about 20 times closer to the star than the Earth is around the sun. Way closer than Mercury's orbit.
Yeah.
Nobody predicted that. It just didn't make any sense, and there was a lot of skepticism about it for a long time, until we got like 10, 20 of these things, and even started to see the transits of these things. And then it was like, okay, everyone now suddenly agrees.
Yeah, this is a thing.
And maybe the same thing will happen with this. A one-off object, it's really hard to give it any context as to how real it could be. But once we start finding more and more of them, and they look similar-ish, perhaps these are always going to be the easiest moons to detect, of course, because they're so big.
Right.
And maybe they're just the tip of that iceberg. It's not surprising that you might find these types of things.
Well, you mentioned that, yeah, this was why was 51 Pegasi, this enormous Jupiter, roughly a Jupiter-sized planet, maybe half the mass of Jupiter, orbiting so close to its star? We don't have anything quite like that in our solar system. And we were picking up one after another of these so-called hot Jupiters. So clearly, hot Jupiters are normal, and clearly our solar system is the oddball. Well, no, not really. It's what we call a selection effect, right? In other words, we have, let's see. Oh, I have to stop the comment beep in Ecamm. Oh, I'm sorry. There's a comment beep going on. I'm not even hearing it, everybody. Okay. So on top of the menu bar, press window preferences and go to general and untick. Of course, I'll be happy to do that. Sorry about that. Let me go. Whoop. We're just figuring out how to do this. That's all.
I didn't know about that either.
I did not.
I'm learning about live stream by a proxy here. How this all works.
Yeah. So I'll go to that. I'll bring up sound effects. I'll go ahead and hit the mute on the sound effects. I hope that helps it. Yeah, and if you don't mind, folks watching, if you don't mind sharing this stream, warts and all, with the public on social media, I'd be very grateful. We'd love to have as many people who wish to join us. And so I'm going to go ahead and get back to what I was saying, and please let me know if we're still getting unwanted sound effects. So the universe wasn't built in a day, says Urban Explorer. He's quite right. It was actually built in a couple of femtoseconds. But anyway, but Nora's live streaming. So what I was saying is that, we discovered that these enormous hot Jupiters are it's seemingly normal, but what we discovered is that's what we call a selection effect. We detected them because they're easy to detect. Hence, you've detected a Neptune-sized moon around a super Jupiter. Undoubtedly, if it's real, it would have been a relatively easy moon to detect. And so this brings up a question that I think was asked a little while ago. I'd like to go ahead and field it to you, David. And that is, you mentioned the TESS spacecraft, which is the Transiting Exoplanet Survey Satellite. Would that be able to detect exomoons or exomoon candidates?
Yes. If you had moons such as this Neptune-sized moon, and they are common, then I certainly think TESS could detect those.
Mm-hmm.
TESS is capable of detecting, already we've seen it prove this, Earth-sized objects. We have Earth-sized transiting planets detected by TESS. So if there are Earth-sized moons out there, then it would have the capacity to detect those. However, I have to say it's probably not the ideal mission for looking for exomoons for a couple of reasons. Um, the first one is that its baseline is rather short. It's looking at each field for about 27 days
Right.
typically, whereas Kepler looked at one field for almost 4.5 years. And if you want to detect these moons, you don't just want to see it once; you want to see it repeatedly, happen over and over again. Now, if you look at the solar system, Mercury does not have any moons. Venus does not have any moons. Once you get to the orbit of the Earth, suddenly all the planets have moons beyond that point. And so, what's the orbital period of Earth? It's 365 days, 1 year. And so that means that Kepler, even with Kepler's 4.5 year baseline, it might have got 4 transits of the Earth
Hmm.
if the alignment was right, that it saw it transiting. And so 4 transits, I mean, that's good. But even that's not ideal. We'd rather have dozens of these things to see the moon coming in and out, over and over again. You almost need a bit of serendipity to catch these moons with just 4 events.
Sure.
And with TESS, of course, it's even worse.
Mm-hmm.
You have 27 days, so you have to be lucky just to see the transit of the planet, let alone the transit of the moon. And of course, one of the ways we actually like to look for moons is through the wobble of the planet. Now, of
Right.
course, one observation, you can't measure a wobble of one observation. You need repeated observations to see it go back and forth, back and forth, back and forth. So we can't detect those wobbles with a single event. So those things are problematic for TESS. However, there is something going for TESS which I'm quite happy about, and that's the extended mission, which it's already entering. We're going to be observing for 2 more years with TESS, and the folks at MIT keep telling us that TESS could run for years and years and years. In fact, its orbit, the rate it's burning fuel right now, I believe it should be stable for a ridiculous, like 200, 300 years.
Wow.
Now, I don't know
Wow.
if CCDs could last that long,
No.
or
Right.
the reaction wheels could last that long is a different question. Of course, with Kepler, that was what happened. The reaction wheels failed,
Yeah.
but it also ran out of fuel with K2 as well. But with
That's right.
TESS's orbit, it's so stabilized, it just basically will never run out of fuel. So that means that we could be doing decades worth of observations, and then that would be very exciting for exoplanes. It just means we have to be patient.
Wow. I had heard orbital stability on the order of decades. First I've ever heard it might be on the order of centuries, which is really remarkable. But yeah, it is such an amazingly clever orbit that they came up with for the spacecraft. And the short version of it, folks, is that it's basically just in a gravitational balance point, or not balance point, but it's in a gravitational hold courtesy of the Earth and Moon, and it just remains remarkably stable. It is such a brilliant orbit. But yes, I did say on the order of between 200 to 300 years. I believe that's what you said, David, right? Is that correct?
Yeah.
Yeah.
I'm just going to try. I know someone's saying that the mic sounds like it's internal. It's actually my webcam mic, but I can try switching back to my original mic, which just to see if that helps a little bit. Because I know you said, Christian, that sounded a bit better.
It was a bit.
Okay,
Yeah.
put back my actual desktop mic. Does that sound any better?
So for those of you commenting, I hope David is sounding a bit better. I think my audio is probably fine, but David is a bit soft. And folks, I don't think that's David's fault. I think that's mine. So trying to sort that out as we go along here.
Yeah, I mean, just so you guys can see what I'm saying, my volume bar is clipping. I keep pushing the volume up, and then the computer keeps going, no, 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 you can't do that. That's you're clipping yourself. It automatically is pushing it back down. So I'm like peaking. My bars are peaking. So I don't think I can talk any louder on my end.
Yeah, so as you can see, I'm using Zoom here, and I'm trying to pipe Zoom through what's called Ecamm Live. That's my streaming software. Gee whiz, David, maybe we should have used Skype. But we'll see. Maybe next time we'll try that.
Okay.
But no, and of course I don't blame the guest at all. Like I said, it's if anybody, it's me, your friendly amateur live streamer on the case here. So
And let's give Christian a break because this is Christian's first time figuring this out. I've done 3 live streams, and I can tell you it's always hairy and something always goes wrong. And it's surprisingly difficult to do. We're astrophysicists, and we like
I'm just an astrophysicist. Yeah, exactly. We're just a couple of astronomers here, guys. But anyway, I wanted to say though, David, that as fascinating as exoplanets and exomoons are, you're also, when you're not doing that and when you're not making videos, you're also coming up with ways of harnessing black holes to get us around the galaxy. And I was just, when I first saw that video, I was blown away by it. I read your paper and I was even more stunned. And I thought, man, this guy is, really smart, and I really, really suck in comparison. So I was wondering if you could tell us a little about what the Halo Drive is, for those who don't know, because folks, you got to check this out. This is really amazing ideas.
Yeah, so I'll give you a little background to where this comes from. There was, I mean, we all have heroes that we look up to, and for me, one of my scientific heroes, who unfortunately he passed away just recently, was Freeman Dyson.
Yeah.
And Freeman Dyson, he you say that I'm versatile and I do exoplanets and black holes, but he was the ultimate. He worked on anything.
He was.
Anything you could think of, he had a paper about it, and
yeah.
It was like a classic paper on the subject.
Yeah, right. He would write the seminal paper on filling the subject.
I was more of this guy, and I found this paper he wrote. There's a fantastic blog that I want to advertise that I read quite often called Centauri Dreams, and it talks about advanced spaceflight concepts.
Mm-hmm.
The sorts of things that we talked about on my channel quite recently with galactic colonization. That's sort of the bread and butter of this blog. So you can just Google Centauri Dreams if you want to catch that. And they did an article on there a few years ago about the gravitational slingshot, which probably many of us have heard of gravitational assists, gravitational slingshots. We use them all the time in the solar system for our own spacecraft. And Freeman Dyson said, hey, what if you did that around 2 neutron stars? And the advantage of that is that neutron stars, because they're so small, they can get really, really close to each other in their orbits. And that means the closer you are to one another, the faster the orbital velocity.
Right.
And so if you slingshot around one of those, you basically steal that orbital velocity, and you can get up to relativistic speeds using this idea. Beautiful idea. But it did have a problem, I felt. And the problem was that you have to fly your spacecraft into the maelstrom of 2 rapidly revolving neutron stars. It's like trying to put your hand in a blender and not get caught.
Yeah, I mean, why would anybody in their right minds get anywhere near one of these things? And now, hey, let's get near 2 of them.
Yeah. I mean, yeah.
Oh, and David, may I ask if you could try switching back to your other mic? Some folks are saying that your other mic might have been a little bit better.
Sure.
But please continue when you're ready.
Okay, I'm back on the other mic.
We'll just roll with it.
Yeah. So this was a neat idea, but it was practically problematic, and I sort of thought about this from the angle of what Breakthrough Starshot were doing. They were suggesting that lasers could be the way forward for interstellar spaceflight. In particular, they wanted to take sort of a piece of tin foil, pretty much, a very thin, flat piece of tin foil, throw a laser beam on it, and that will push the tinfoil away through radiation pressure. You want it to be something very light and reflective. That's sort of why something like tinfoil might work.
Sure.
Obviously, in reality, it's something a bit more advanced material than tinfoil.
Right.
But that's kind of the basic idea. And I thought, well, maybe we could do something like this with Dyson's slingshot. And the idea is to swap out those two neutron stars, make one of them be a black hole. So you have two rapidly rotating objects. And now, because light will deflect, it will bend around a black hole, you can actually choose a trajectory for the light such that it skims the event horizon of the black hole, and it doesn't quite fall in. It's not quite deep enough to go into the black hole, it's just to the outside, and so it will bend all the way around. It will do a 180, and it will come back to you. That's called a boomerang geodesic, and it was discovered by William Stuckey in 1993. And I thought that could be neat. You could use that here. So instead of flying our spaceship into this spinning maelstrom, we stand way outside, we fire our laser beam in, it bends round. And this creates the following effect. When you fire the photons initially, that pushes your ship away, just due to the momentum balance.
Right.
The photons then loop around, they come back and they push you again, so you get two pushes. And because this light went around the black hole, which is moving, if you choose the moment right, you can choose it where the black hole is moving towards you. That's kind of like throwing a ping pong ball off a wall that's coming towards you. The ping pong ball will come back faster.
Yeah.
And the light
get more energy.
come back with more energy.
Yeah.
And so it actually ends up becoming blue shifted, carries more energy inside it. So not only do you propel your spaceship, you actually you get more energy out than you put in.
Right, you get a gravitational blue shift. And
exactly.
Yeah.
So this isn't even a gravitational blue shift. A gravitational blue shift, I mean, when the light falls towards the black hole, it will gravitationally blue shift.
Yeah.
In addition to this effect. And then when it comes back out again, it will gravitationally redshift. But those two cancel out completely.
Okay, I see what you're saying.
Net zero to be had with a gravitational shift and blue shift.
Okay, but
this is different. This is actually a special relativistic effect.
Is this relativistic beaming?
Coming off a moving frame of reference, and that's giving you this blue shift.
So this isn't relativistic beaming, is it?
No. So relativistic beaming is normally when we talk about relativistic beaming, it's actually relevant to exoplanets. That normally means that there's a luminous source which is moving towards you, and the luminosity of that source appears enhanced.
I see. Yes.
A combination of relativistic aberration, which is when the light cone sort of squeezes down towards you, and there's also like a spectral effect which can happen as well, because the light source is a Planck function if you look at its spectrum, and that also shifts towards the blue, and so in a finite bandpass you can get more flux inside.
Oh, okay.
Technical, maybe overly technical description of it to describe in one 30-second description.
No, yeah, right. That's a taste of it.
It's a different effect.
So Raj Luthor was asking, how fast can you go with the Halo drive?
Well, you can go up to, I'm trying to remember the numbers from the paper now. I think it was something like 150%, I'm thinking off the top of my head, 150% of the speed of the black hole itself. So these black holes can be moving very, very fast. For a classical slingshot in the solar system, the theoretical maximum slingshot you can ever perform is exactly twice the velocity of the planet. That's the maximum velocity you can steal. You can never, in reality, ever get that, though, because that means that you kind of have to do a perfect 180. You have to kind of skim the atmosphere, but if you skim the atmosphere, that would slow you down.
Then you lose energy. Right.
So it's kind of tricky to ever realize such a huge delta V in the solar system. And similar effects come into play here. So in theory, it should be twice the speed of the black hole, which can be anything from, for these extreme black holes, they can be like 0.1, 0.2 C. So you're talking about 10-20% speed of light. And you're getting 50% more than that, so you can get up to relativistic speeds, as we'd say, sort of 30% the speed of light. And the reason why you don't get exactly 2 is because of some small losses which happen during the journey, which may be a little bit too technical to get into, but that's similar-ish to what happens with planets. You can never get the full factor of 2 out.
Fascinating. So point is that this is plausible. It's physically possible. Obviously, there are some minor engineering challenges to overcome, not the least of which is surviving in that environment, shielding yourself from the radiation, which you'd undoubtedly be contending with, and just generally the ordinary boring bits of having to stay alive in such an environment. But wow, I thought it was just an amazing idea, and it was just absolutely brilliant. And I just loved the fact that you took the time to put it together as a video. I mean, why not? It was just such a lent itself just beautifully to a video. And if you haven't seen it, folks, please head over to David's channel. Check out the Halo Drive video. Just subscribe to his channel. You'll be better off for it. Speaking of videos, I know that's something you've been interested in. Of course, I think everybody who ever gets curious about the cosmos gets interested in is, where is everybody? Where are the other aliens? How come are we really alone? And you've done a couple of videos where you talk about that, and I thought you articulated, if not the argument, at least the possibility that we really are alone in the universe. And I was wondering if you could talk a little bit about how you arrived at that. I don't want to say conclusion, but arrived at that potential determination.
Well, yeah, I want to clarify. Sometimes people do get the wrong end of the stick when I talk about this.
Yeah.
My opinion, my view on this is not that we are alone in the universe, and it's not that we live in a crowded universe. It's that I don't know. That is most honestly my answer to that question. And I just really wanted to push back a little bit against, I read a lot of proposals, people writing papers and proposals trying to get grant money. And there's almost a default assumption very often, even amongst scientists, that it's not a question of if we will find life, it's just a question of when we will find life. So certainly it's sort of treated as, of course we will. But in a way that sort of devalues the experiment. Like, why do the experiment to look for life if you think you already know the answer? I mean, why would I give you $10 million to do an experiment where I'm going to say, I'm going to drop this phone and it's going to forward you to gravity?
Right.
Like, well, yeah, like, if it's already a known thing, it wouldn't be worth funding an experiment to do it.
Right.
So I kind of have a somewhat of a problem just with the framing of it. I think it actually can hurt us as people trying to excite the community in the world about what we're doing. I think it can actually hurt us if we pretend that we already know the answer to something when we honestly don't know the answer to this question.
We seem to have a single data point.
If you say I don't know, then you have to admit the possibility, just the possibility that it is at least possible that we could indeed be the only example of intelligent life, perhaps in our Milky Way galaxy, or maybe we're even the only example of life, period, in the galaxy or in our local neighborhood. Who knows? And there's good reasons to think that. I mean, there's been a lot of work to think about, like the rare earth hypothesis, for instance, the series of events which culminated in our own planet being formed, the origins of life on the Earth are not well understood. It's really deeply unclear if it was a fluke or if it was an inevitable outcome. I could accept either. I don't really have a view either way. I'm going to let the biologists figure that out. But I'm not closed-minded that I'm going to say it has to be inevitable.
Right.
I won't accept an answer that is the other way. And I think there is a resistance to that, and it can bear from our own personal biases, I think. If you believe in something before you even get started in something, it can subconsciously creep in and influence your scientific framework. I think about it a lot looking at exomoons.
Right.
We're looking at exomoons, and of course I want to find one. And the very fact I want to find one should give me great pause for thought when I think I found one.
Yes.
Because I am biased. I know I'm
Right.
biased.
Right. You know what you're looking for, and you see it.
I have to work really hard to correct that bias back the other way. I can't assume that Neptune-sized moons exist just because, hey, why not? Nature's surprising. That's not enough of an argument to say, therefore, this is real. It has to be more than that. And so it's just an issue of caution for me. It's just sort of treating it as an open question until we've actually got some data to prove it one way or the other.
I agree with you on that 100%. And first of all, I just want to say thank you so much to Surrogacy for the super chat of $5 Australian. Thank you so much, Surrogacy. It's appreciated. Every little bit helps. Unless you're a student, in which case I don't want your money. Students, save your money and become productive members of society. But thank you very much. David, I think I'm glad that you bring this up because I think when it comes so much to science communication, and I know that I'm guilty of this, and I think we all are to some extent, it's easy, especially in the shorthand formats of public speaking or YouTube or anything like that, it's easy to just deliver it as a given that, here is what we know as if though we are 100% sure that it is true. And yet, if you've ever read, and you, dear viewer, if you've ever read a scientific paper, you'll see loads and loads of caveats, or at least the good papers will have loads of caveats and assumptions, and they'll list things like uncertainty in the measurements, uncertainty in the analysis, potential biases. We are all human, and we do bring our preconceived notions of things. So I thought, David, when you got to talking about things like the Fermi paradox, are we alone, treating it as that a proper scientific question, the only answer that we have is we don't know. We have a single data point. Here we are. And even going so far as to clarify what it is we mean when we say life, because we take these things for granted. And I think at the end of the day, I'm not a biologist either, but, we know what life is when we see it. I think, if I may ask you, David, when you're talking about finding life elsewhere, I think are you constraining yourself to intelligent life, or do you think it's possible that life could be elsewhere, just in a simpler format? Is that a potential solution to the Fermi paradox for you? And again, I know this is just your opinion, so
Yeah, I mean, well, I can say whatever the probability of life starting on a planet is, the probability that planets also have intelligent life on them, whatever you mean by intelligent life, of course, or even life, to be fair. There's a big definition thing here.
Right.
But just take that as a given for the moment. The probability of intelligent life has to be less than the probability of life.
Right.
Or at least equal to. It has to be less than or equal to.
Sure.
I mean, that's the most optimistic view, is that every single life origin eventually spawns an intelligent civilization.
Right.
I think very few, even amongst my colleagues, would buy into that. Even the most optimistic would think that it's inevitable that once you start life, a civilization will emerge. I mean, a very obvious reason for that is just lifetimes of stars and planets. So many stars live much younger, much less time than our own star. F-dwarfs, for instance, typically live for 1 or 2 billion years.
Mm-hmm.
And if you reran the clock on Earth on one of these F-dwarfs, if what happened on Earth was typical, which we don't know, but let's assume it was for the moment, if it was typical, then we would not emerge on that planet, because the planet would not remain habitable long enough for us to ever emerge on that system. So certainly it makes sense to me that if there is life out there, there's probably more life than there is intelligent life. And then when we talk about intelligent life, that's such a broad, interesting question to dive into. I mean, is a dolphin intelligent life? Is a humpback whale intelligent life? Are we calling it just technology? And what about technology? Does it have to be a technology that's spacefaring or communicative?
Right.
Maybe they're just xenophobes. So this is, of course, the whole history of Fermi's paradox, is that
Right.
there's a million and one ways to get around it. And that's why it's a frustrating yet intellectually very stimulating problem to think about. It's a question we can't resist thinking about. Yet at the same time, we know that there's so many ways that you could get around it, but it's a compelling question.
It really is, and I think that's something else that people tend to want to know. I mean, we all want to know. I think the best we have right now, or the best tool at our disposal, is, well, coming up with ways of thinking about properly framing the question and thinking about ways of investigating the question. And we certainly have done that in the past. We've certainly, done the search for extraterrestrial intelligence. But just to take that as an example, the definition of an intelligent civilization is one that is broadcasting in the radio part of the spectrum. That's a very, if you think about it, that's probably a narrow, that's probably a very narrow definition.
Yeah, I
You know.
mean, certainly even now,
Oh,
many people have pointed out that our own communication methods are evolving. I mean, we even have written a paper about this in my team, thinking about, again, using lasers, optical SETI is a whole field now, thinking about how there might be alternative ways of communicating, and even there's now papers thinking it's neutrinos, gravitational waves, perhaps even. It seems, fanciful for us to imagine communicating through gravitational waves.
right.
But maybe it's such an efficient method for an advanced civilization that they would never dream of using radio waves. I mean, gravity waves travel at the speed of light, after all, so they're just as fast.
And they're going to get through everything.
Maybe for them it's an obvious way of doing it.
Well, I was going to say, the gravitational wave, would there be nothing that could interfere with the gravitational wave? There'd be nothing that can block a gravitational wave. You're talking about the bending and relaxing of space-time itself, rippling, rippling through space-time. What's going to block that? With radio, it could be potentially blocked. There could be interference. It's hard to interfere with the gravity wave except with other gravity waves. And by the way, thank you very much, Pusa Studios, for the $5 super chat. Thank you so much up there in Montreal. Hope you guys are doing well and staying happy and healthy. So, David, I wanted to just talk with you a little bit about this other question about colonizing the galaxy. This is the topic of your latest video, and I thought that was a really interesting way to look at this. I mean, basically, it's more of a mathematical question than anything else. But you were speaking with somebody who's actually done some research. I was wondering if you could tell us a little bit about your conversations with them and what you learned from that.
Yeah, this is with Professor Jason Wright. Professor Wright is really one of the most eminent SETI researchers active today. Probably many of you have heard of the names of Jill Tarter and Frank Drake, and even Carl Sagan was, your key names in the search and thinking about extraterrestrial life. There's been a real renaissance of interest in SETI recently, partly because of new funding arriving through private foundations, such as the Breakthrough Foundation. There's now this Breakthrough Listen project. $100 million is being invested to conduct. Already they've searched far more of the sky and the radio wave bands than has ever been done before, looking for extraterrestrial signals. And at the same time, Penn State and Jason in particular have been also galvanizing a lot of interest. Jason's been very active. He worked on the Tabby star, which I'm sure many people heard of. He's been thinking about looking for Kardashev civilizations, Dyson spheres. He's been actually conducting searches for them with infrared telescopes. He didn't find any. Even for Kardashev galaxies, essentially, entire galaxies which are anomalously infrared bright but optically dim.
Oh, wow.
Implying that every star has been converted into a Dyson sphere. And he even can put upper limits on the fraction of galaxies which are converted into Kardashev civilizations. And again, the answer is apparently not very many, right? So I mean, this is why I don't want to say I'm a pessimist.
Yeah.
But this is why I certainly don't think the universe is teeming with advanced civilizations, because there's a lot of data we're collecting that just time and time again it just keeps hitting up a null. Anyway, me and Jason, we talk often about SETI, and we've written white papers together, proposals together. And we're even organizing a meeting that unfortunately just actually pushed back, of course, like many meetings.
Sure.
On set at the first Penn State SETI meeting that we were just going to organize this summer. And we got talking, and I heard about his new work, and he was thinking about how does a civilization spread out through a galaxy. And the real new thing that he's done, that people have thought about this problem for a long time, and they've often typically assumed that the stars are fixed. Stars don't move.
Right.
And you just sort of jump from one star to the other, you colonize it, and then that colony can maybe, it's almost like microbial growth. It just sort of spreads out through the petri dish of the galaxy and eventually takes over the whole galaxy. And what he wanted to do was include moving stars, because of course in reality they do move. and they actually move quite fast. And if your ships are slow, then the star's movement might even be comparable to the speed of your ships. And thus it makes a really big difference. And in fact, in a way, the stars are your starships. They carry you from place to place across the galaxy for free.
Yeah.
You don't need to build a giant rocket. You just have to make that little hop
Right.
from your star to the nearest star, and that's about it. And that's enough over a long period of time to sort of diffuse the civilization across the galaxy. So he did a really interesting paper on that with a postdoc at Rochester University, and Adam Frank was also on that paper. And I was intrigued by their work. I managed to sat down with Jason. We talked about it, and I think it's a really compelling constraint. The fact that the Earth is clearly not colonized, as far as we can tell. That's an interesting constraint. It means there are some. It doesn't really matter what you assume about. Maybe we're not listening in the right radio band, or maybe they're using optical SETI rather than radio SETI. Or, maybe there's some communication misstep happening. This isn't anything to do with communication. They don't care about communication.
Right. This is just about getting there.
Maybe a rampant AI that's just going across the galaxy, just swallowing up all the planets and turning them into computer substrate. And physics tells us that that should be allowed. And as far as we can tell, the technology is not ridiculous. So it's really intriguing that clearly hasn't happened yet. As far as we can tell, it should be possible for it to happen. And that's what the video really gets into.
I thought it was such a fascinating conversation, and I really would like to see more of it. I'm glad that you were in the process of organizing a conference on that, and that's it would have been up at State College, is that right?
Yeah.
Pennsylvania? Well,
obviously we're going to probably delay it a year now. But
yeah, well, let me know. I mean, I'll be there. That's not too far from where I live. There were a couple of questions, and folks, I'm sorry if I haven't invited you to ask questions, but please do. I know David's got another commitment this afternoon, so I don't want to hold up too much of his time. But for the next few minutes, there were just a couple of quick questions I just wanted to pass along here. I thought this was a pretty interesting one, David, particularly if you've, I don't know how active you are in ground-based work, but Urban Explorer asked, with there being 99% less planes in the sky and less pollution, is now a good time to look up there? Interesting question. I have some thoughts on that, but go ahead, Dave, with yours.
Well, yeah, I'm not a ground-based observer, so this is coming from a slight position of non-expertise. But I've certainly seen. I have done a little bit of observing from the ground, and I've seen aeroplanes in the images. They're pretty obvious. I mean, there's not much risk of you not noticing an aeroplane in your image. So they're very easy to remove from your data. And it's pretty rare that you get them, but they do happen. You do sometimes get, an airplane in your image. I don't know what the contamination rate is, though, off the top of my head.
I'm not sure either.
But my feeling is airplane traffic has not, unless your telescope's next to an airport. I don't think it's a significant issue. I think what a lot of astronomers are more concerned about is maybe Starlink and putting up lots of satellites. When you talk about filling the entire sky with satellites, there's been more concern, at least amongst my colleagues, about what Starlink's doing rather than airplane traffic. But certainly the pollution aspect is another interesting. Again, most of the observatories we use are not in polluted areas.
Right.
Maybe 100 years ago, 200 years ago, telescopes were in cities. We have one even in New York, and on top of Columbia, we have a telescope. So maybe from there, actually, the data has suddenly got really good.
Yeah, I'm sure we're going to do a better job from Towson University.
But it might be possible the data has improved in New York City. But most of the telescopes we, of course, use tend to be, Mauna Kea or in Chile, in remote locations where hardly anyone or any pollution is present. So I don't think the data would be significantly affected.
I agree with you too, David. I don't think you're going to see a huge quote-unquote improvement in data because there are fewer flights these days. I do agree they're relatively uncommon, but one thing I understand, and I could be wrong, but my understanding is that a number of ground-based observatories are closed up because of the the risk of getting people out there. So
Yeah.
this is on the one hand, this is as good a time as any to do it. But on the other hand, when you have a situation where people can't even get out, or if they're in shutdown areas, so you have some ground-based observatories in the Southwest. My understanding is that their operations are on hold. One of my best friends is an astronomer at the University of Wyoming, Mike Brotherton. If you're watching, buddy, how you doing? And if he is watching, I can assure you he is watching from atop Gel Mountain, because in order to isolate himself from his wife, who works in a nursing home, you see where this is going, he's decided to head up the mountain and stay there. So he's getting his work done. He's getting his observing done. And I'd say that if you happen to be in a situation where you happen to have an observatory to yourself, this is a great time. But if you don't have access to your own observatory, this might be a bit of a frustrating time. But I think as far as just generally going out and stargazing, yeah, I mean, to me, it's no better or worse than normal. I don't think you would notice any particular improvement in your observing conditions. One other question that I thought I saw here was from Raj Luthra, and perhaps pardon me for going back a few steps in our conversation, but what are your thoughts on the EM drive?
Oh, the EM drive. I mean,
Yeah.
I haven't even really spent much time or energy thinking about that, to be honest with you. I think to me it falls in that category of the fact it violates, fundamental principles of thermodynamics and momentum conservation. Sort of put it at such a deeply skeptical position for me that unless I see overwhelming evidence that it's performing, not. I think there's been tests where they show that it produces like maybe 3 nano, whatever the units are, units of thrust. It's like absolutely imperceptible,
Right.
and plus or minus like 1.5. So it's like a 2 sigma effect. If it was like an overwhelming force and this thing was flying across the room,
Right.
I'd be interested. The fact it violates these fundamental principles. I mean, there's such a long, long history of perpetual motion machines that physicists. I mean, at Columbia, I get messages like that, or we get letters, handwritten letters, where people who think they invented
Yeah.
a new drive of some kind, or that violates everything that we know about physics, or Einstein's wrong. That's a really common one we get. And sometimes I'll
Yes.
look at them, but honestly, we get so much of it. If it violates known laws of physics without any overwhelming experimental evidence, it's very hard to give it your attention.
Right.
Extraordinary claims require extraordinary evidence. This is a very extraordinary claim, and it lacks extraordinary evidence, in my opinion. So
I
this is
agree.
why I'm not giving too much of my time.
No, I agree with you there. I mean, I'll say this: at least there was some effort made at producing this in a lab, or at least that's what's been claimed. But yeah, I mean, as opposed to just conjecture, you know.
Yeah,
But yeah, this was as you said, it was extremely the effect that they claimed to have measured was really in the noise, and 2 sigma significance is really nothing. So yeah,
yeah. This kind of reminds me of like the opera experiment where we heard about faster than light neutrinos for a
yes,
while.
yes,
And
good
it
one.
was if you weren't scientifically trained, you might have taken that on face value and said, "This is great. We've faster than light neutrinos, great." But anybody who's ever done a scientific experiment knows that even your error bars are not real, and they're probably underestimates of the true error bars.
Right.
And indeed, that's what happened. There was just an error somewhere in the pipeline that they hadn't accounted for. And when you accounted for that error, then it turned out it was just a systematic offset that was explaining it. It wasn't anything real. So I think just with physicists, a lot of us have seen it so many times and seen it, unless it's a huge effect, unless it was going like twice the speed of light, then maybe it'd be like, hold on, this is a big effect. But when you're talking about 0.0001 c, and the measurement is so noisy, it's not convincing, and it violates everything we know about physics. That you need better data than that to convince me of your physics breaking experiment.
Well, I also think that to the credit of the physicists who came up with this potential FTL neutrino problem, they even went ahead and said, "Hey,
Yeah,
this is what we're getting. We don't think this can be real, but we don't know what we're doing wrong. And it actually took a lot of people quite some time to figure it out. And that to me is exactly the way to approach these sorts of things, as opposed to claiming, hey, I've discovered a reactionless drive. Hey, I violated conservation of momentum, and Einstein was wrong, and all that kind of stuff. It's like, no, 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 no. That's not how science works. Science
Yeah,
doesn't work with.
I don't blame the scientists involved in any way. I think the way they've handled it was exactly correct.
Yeah,
They
with the
should
neutrinos. Yeah,
they had to report it. They had to report it. It was amazing. It was a very interesting result, so it had to be reported. Of course, when you report a result like that, there is inevitably going to be a headline written in some lowbrow newspaper that will just remove all of that detail and just say faster than light neutrinos detected, and that's it, and
yeah,
that's where the damage is done to science.
yeah.
Is
Unfortunately.
that step between the scientists and often not all journalists, but sometimes this does happen, as you all know.
Well, I hope that thanks to your channel and hopefully from mine as well, hopefully we're able to kind of clarify some of these things just a little bit here and there as we go along. But David, I really do want to thank you very much for coming out here today. And folks, again, my apologies to all of you for the sound problems. I promise we will get these resolved. We will continue to do this because I'm thinking, now that we're kind of in, we may as well do these sorts of things a little bit more often. I'm thinking maybe once every Saturday afternoon we can get together and kind of have lunch like this and just chat and just kind of have some fun while we're at it. But I do promise to get these audio issues resolved. Once again, I'd like to thank my guest, Dr. David Kipping. And if you haven't yet, please do check out Cool Worlds on YouTube. It's a wonderful channel.
Thank you to everyone for tuning in
Yes.
and your patience with us figuring out the sound quality. Going live is always, it's always a little bit hairy, so we appreciate you hanging out, and I enjoyed our conversation today. A lot of fun. Happy to come on again.
I'd love to have you back, man. That would be great. And everyone, thank you all again. And the whole tick 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 thing with the wow, that's news to me. We don't even hear it. David and I don't even hear it. So we definitely got to resolve that. But we'll make it work. I think we're we're reasonably intelligent people, but you guys are even smarter, and therefore I'm sure between all of us we'll get this thing sorted. So thank you all very much, everybody. Please stay home, stay healthy, and to borrow from my friend David here, stay thoughtful and stay curious, my friends.
Absolutely.
Thank you so much,
Thank you
everyone.
very much, guys. Pleasure being here.
Cheers.
Bye.
Let's see. I think we're out. I really hope we are out. I'm watching myself. I pressed end stream on YouTube, and I think
Just a delay.
I think it's the delay because they're still talking. But yeah, I think. Well, I'm gonna finish my eCam here. No, we're still on. Bye, everybody.